Hello! I'm Professor Von Schmohawk, and welcome to YU. In the previous lecture, we saw a number of examples of exponential functions. We said that exponential functions appear in many fields such as science, medicine, and business. Exponential functions were first explored by the Swiss mathematician Jacob Bernoulli in 1683 as a way of computing continuous compound interest. His research led to the development of the exponential function, whose base is the constant e, also known as Euler's number. Although e is an irrational number and therefore cannot be expressed by a finite number of digits, the constant e is approximately equal to 2.718. As we saw in the previous lecture, an exponential function's base may have values other than e. In fact, an exponential function's base may be any positive real number other than 1. So to understand how exponential functions are used to compute interest, let's start by looking at the difference between simple interest, compound interest, and continuous compound interest. The most straightforward type of interest is simple interest. Mortgages and personal loans often charge simple interest. Simple interest is a fixed charge paid to the lender for the use of money over a given period of time. For example, let's say your Uncle Moneybucks agrees to loan you $100 for 1 year at 12% interest. However, at the end of the year, you must pay back the money you borrowed plus 12% interest, which is 12% of $100, or $12. Likewise, let's say you wanted to borrow $100 at 12% annual interest, but you weren't sure how long you needed to wait before you could pay back the loan. In that case, you might prefer to break the annual interest payment into 12 monthly payments of 1% each month, and at the end of any month, you could decide to pay off the loan. So let's see how this would work. Once again, Uncle Moneybucks loans you $100. At the end of each month, you pay interest of 1% of $100 or $1 of simple interest every month. If after 3 months you decide to pay back the $100 loan, you will have paid only 3% simple interest for a 3-month loan rather than 12% annual interest. So now that we understand simple interest, let's see how compound interest differs from simple interest. Let's say that you decide to deposit $100 into a savings account that pays 1% simple interest each month. Every month, the bank will send you a 1% interest payment on your $100 deposit, so you receive $1 of interest each month. By the end of the year, you will have accumulated $12 of interest so you now have a total of $112. But what if instead of receiving $1 of interest each month, the interest was automatically added to your savings account? Would you still end up with the same amount at the end of 1 year? That method of adding the accumulating interest to the principal is called compound interest. So now let's say that you deposit $100 into a savings account that pays 1% compound interest every month. Each month, your savings still earns 1% interest. But with compound interest, instead of sending you an interest payment, the interest is automatically added to your savings account. Now each month, your interest will be calculated on a slightly larger amount of savings. Therefore, in month 2, the interest generated is 1% of $101. 1% of $101 is $1.01. So your savings at the end of month 2 will be $102.01. Now, the next month, your interest will be calculated on an even larger amount of savings. So in month 3, the interest generated is 1% of $102.01. Each month, the interest generated with compound interest will be slightly larger than the interest generated with simple interest. By the end of 12 months, you will have accumulated $112.68. So with 12% annual interest compounded monthly, after 1 year, you would end up with $112.68, 68 cents more than you would have earned with simple interest. In fact, with this same compound interest rate over 5 years, the savings account will have accrued $20.67 more than with simple interest. Even if the simple interest rate were increased to 16%, the account would still not produce as much income as with 12% compound interest. In the 17th century, Jacob Bernoulli had become interested in the idea of compound interest. He wondered what effect the frequency of compounding has on the growth of the initial investment. If you increased the number of compounding periods in a year, would this produce more income, and if so, how much more? To answer this question, let's start by creating a formula for the amount of interest produced after several compounding periods. We can use a simple example of compounding annually for 3 years. Let's say that we deposit money in a savings account that compounds interest once a year. To calculate how much our principal will grow, we will need to know the initial principal amount, which we will call P, and the annual interest rate, which we will call R. So the interest generated in the first year will be the initial principal multiplied by the annual interest rate. Since the interest is compounded, this interest is then added to the principal. So the principal at the end of the first year will be the initial principal P plus the first year's interest. Factoring out the 2 copies of P, the principal at the end of the first year is P times 1 plus R. Since the principal is now grown, the interest generated in the second year will be greater than the interest generated in the first year. Now, the interest generated in the second year will be the annual interest rate R times the principal from the first year. And the principal at the end of the second year will be the sum of the principal at the end of the first year plus the additional interest generated in the second year. We can simplify this expression by factoring out the two copies of 1 plus R and the two copies of P, and then write 1 plus R times 1 plus R as 1 plus R squared. Now, to calculate the third year's interest, we multiply the annual interest rate R times the second year's principal. So the principal at the end of the third year is the sum of the second year's principal plus third year's interest. We can then simplify this expression by factoring out the two copies of 1 plus R squared and the two copies of P, and then write 1 plus R squared times 1 plus R as 1 plus R cubed. So after one compounding period, the principal will be P times 1 plus R to the first power. After two compounding periods, the principal will be P times 1 plus R to the second power. And after three compounding periods, the principal will be P times 1 plus R to the third power. So given an initial investment of principal P that earns compound interest once a year at an annual interest rate R, the principal's value after 1, 2, or 3 compounding periods will be P times 1 plus R, where the exponent of 1 plus R is the number of compounding periods. This formula will work for any number of compounding periods. Therefore, we can write this formula in a more general way by making the number of compounding periods a variable such as t. This formula can be modified to work for quarterly compounding by making two small changes. With annual compounding, the interest rate for each compounding period was R, the annual interest rate. But with quarterly compounding, each year is divided into 4 compounding periods, so the interest rate for each compounding period will be 1/4 of the annual interest rate. Additionally, we must modify the exponent of the expression in parentheses. The value of this exponent must be the total number of compounding periods. Since with quarterly compounding there are 4 compounding periods per year, the exponent must be 4 times the number of years t. With these modifications, we now have a formula that tells us the amount of principal after t years of quarterly compounding. Now, if we wish to modify this formula for weekly compounding, since there are 52 weeks in a year, we simply change the 4 to 52. Likewise, with daily compounding, there are 365 compounding periods each year. So in general, if there are n compounding periods per year, the formula for the principal after t years will be P times 1 plus R over n with an exponent of n times t. Now, like the great Jacob Bernoulli, let's calculate how the growth of principal is affected as we increase the number of compounding periods per year. We will use this formula several times, each time increasing n, the number of compounding periods per year, to see what effect this has on the principal at the end of 10 years. In each of these examples, we will assume a $100,000 initial investment invested at an annual interest rate of 12% over a period of 10 years. So in each example, everything will be constant except for n, the number of compounding periods per year, and by increasing n in each new example, we will see what effect this has on the principal growth at the end of 10 years. So like Jacob Bernoulli, let's see how our investment growth changes as we increase n, the number of compounding periods per year, thereby decreasing the length of the compounding periods. We will start by calculating the amount of principal growth if interest is compounded annually during the 10 years. Since the principal is compounded once a year, n, the number of compounding periods per year, is 1. The exponent 10 times 1 is then 10, and 0.12 divided by 1 is 0.12. Adding 1 to 0.12 gives us 1.12. And 1.12 raised to the 10th power is approximately 3.10585. Multiplying that times an initial principal of $100,000, we see that with annual compounding, after 10 years, our initial $100,000 investment has grown to $310,585. Now, let's see how this compares with quarterly compounding. With quarterly compounding, the principal is compounded 4 times a year, so n, the number of compounding periods per year, is 4. The exponent 10 times 4 is 40, and 0.12 divided by 4 is 0.03. 1 plus 0.03 is 1.03. And 1.03 raised to the 40th power is approximately 3.26204. Finally, multiplying that number times the $100,000 initial principal, with quarterly compounding, our initial $100,000 has grown to $326,204. Compared to annual compounding, compounding once a quarter produces $15,619 more than compounding once a year. Now let's see how this compares with monthly compounding. With monthly compounding, the principal is compounded 12 times a year, so n, the number of compounding periods per year, is 12. The exponent 10 times 12 is 120, and 0.12 divided by 12 is 0.01. Adding 1 gives us 1.01, and 1.01 raised to the 120th power is approximately 3.30039. Multiplying times the initial principal, with monthly compounding, our initial $100,000 has grown to $330,039. Compared to quarterly and annual compounding, although quarterly compounding produced $15,619 more than annual compounding, Monthly compounding produced a smaller improvement of $3,835 more than quarterly compounding. In fact, if we continue to reduce the length of the compounding periods, we see that compounding once a week produces only about $1,500 more than compounding once a month. Compounding once a day produces $392 more than compounding once a week. Compounding once an hour produces $63 more than compounding daily. And compounding once a minute produces $3 more than compounding hourly. We can see from this that reducing the compounding period, thereby increasing the compounding frequency, increases our investment return, although by smaller and smaller amounts. This is easy to see with a graph of principal versus time for several different compounding periods. Graphing the growth of the $100,000 principal over 10 years with annual compounding, we see that each year the principal grows at an accelerating rate, ending up with an accumulated principal of over $310,000. Graphing the principal growth with quarterly compounding, we see that each quarter the principal also grows at an accelerating rate, ending with a larger principal of over $326,000. And graphing the growth with monthly compounding, each month the principal also grows at an accelerating rate, ending with a slightly larger principal of a little more than $330,000. Bernoulli was able to show that as the compounding periods continued to decrease, the resulting return on investment approaches a limiting amount. Using calculus methodology that had recently been introduced by Isaac Newton and Gottfried Leibniz, Bernoulli developed a mathematical process to calculate the total interest generated if the compounding periods were infinitely small. This way of calculating interest is now called continuous compound interest. Bernoulli's formula for continuous compound interest was based on the exponential function, a new mathematical concept at the time whose base was an irrational constant that we now call E, otherwise known as Euler's number. The exponent of E in Bernoulli's formula is RT, where R is the annual interest rate and T is the number of years of continuous compounding. To calculate the final value of an investment, this expression is multiplied by the initial principal amount, P. We can apply this formula to our previous example by setting the annual interest rate R to 12%, and the initial principal P to $100,000. If we graph this exponential function over a range of values for t, we can see how our investment would grow over time with continuous compound interest. Starting with an initial principal of $100,000, we can see that with continuous compounding, the principal grows at an accelerating rate following an exponential curve, until after 10 years, the principal has grown to $332,012. The growth of principal continues to accelerate with time. After another 5 years of continuously compounded interest, the initial principal will have grown to over $600,000. Comparing continuous compounding to our previous results from non-continuous compounding, compounding once a minute versus hourly, increases the principal by $3 more than hourly compounding. And although compounding periods shorter than a minute seem to provide no improvements in principal growth, if we calculate our results out to a few more decimal places, we see that compounding once a second versus once a minute increases the final principal by about 4.5 cents, and compounding continuously increases the final principal by about 0.08 cents more than compounding once a second. So with continuous compounding, the compounding periods can be thought of as being infinitely short, with the increase in principal approaching the theoretical upper limit. And in Bernoulli's quest to determine this upper limit, his work led to the development of the first exponential function. In the previous lecture, we said that exponential and logarithmic functions were two closely related transcendental functions. In fact, logarithmic functions are considered to be the inverse of exponential functions. In the next lecture, we will show how logarithmic functions work and why logarithms are the inverse of exponentiation.